Hey guys, welcome back. Uh, so, so let's review a few things we learned in the last class. Some of the things we learned is about the electric potential, right? So just to review quickly, if we have 2 points, point A to point B, and then if there is these points are in the uniform electric field, and this let's say these 2 points are at a distance some d, and if we want to move a charge, if we place a point charge, some charge q here, work the field has to do the work to move this charge from point A to point B, right? So the work is basically the amount of energy, potential energy changes here, right? So the amount of energy, potential energy needed to move charge from one point to another point in a space is called electric potential, right? So we talk about this, and we wrote delta V equal to delta U over Q, and then for this was the definition of the electric potential, right? Remember, this is a potential difference. Delta V is a potential difference. It's a function of 2 points, okay? So we need to have 2 points to talk about the electric potential, and then unit is volt, right? We also looked at the electric potential for a point charge. It's just written as V, even though it is the change in electric potential, but we just write it V, okay? Even though this is just written as V, but this is actually change in electric potential, okay? Just for point charge we write V, and then we saw that V equal to KQ over R for point charge. So basically, when we have a point charge, what happens is we know one point, right? Like we can say, okay, maybe in this case, let's say we have just a point charge. We may have, this point B may not be there, but then we have this point charge. So what do we say is like we are trying to bring this point charge from infinity to some distance, some point, this point, okay? That's how we talk about the electric potential for a point charge, okay? So this turns out to be equal to KQ by R. We also looked at the important, we also learned about important concept, electric equipotential surfaces. Remember, so there are properties. There are some properties of these surfaces, okay? And then we did some practice with the equipotential surfaces, right? So equipotential meaning equal potential. Here is the term. Equipotential surfaces, these are the surfaces where the value of electric potential is constant, okay? So V is a constant along equipotential surfaces. Equipotential surface is perpendicular to the direction of electric field. So if we have electric field lines, like electric field pointing like this, equipotential surface would be perpendicular to that, okay? It looks like a dashed line, but however this is not a line, it's a surface. It's like this. If we have a field, uniform field going like that, and then the electric field direction is this way, right, along these lines, then this equipotential surface would be something like this sheet of paper like this. Now when we make it in the diagram, it looks just dot, because we are just looking at only this part of the, we can draw only this, right, because that's what we can do in the 2 dimension, okay? So That is another property of equipotential surfaces. We also talk about, and then another property is the electric field lines always goes from higher electric potential to lower electric potential, and we said the region where we have a positive charge is a region of a higher electric potential, and if we have a negative region with the negative charge, that would be the lower potential, okay, region of lower potential. And then we also looked at E is equal to delta V by D, right? So, or you can just write delta V equal to E d, whichever is easy for you to remember, even if okay. So electric field, electric potential, they are related, but the key difference is electric potential is a scalar quantity, electric field is a vector quantity. Okay, so those are different things to note down. We also looked at equipotential surfaces for few of the charge distribution, and then this is what it looked like for a point charge. It would be just a series of concentric spherical surfaces, right? This is if we have this point charge here. So this red dashed line is going to be the equipotential surfaces. So basically equipotential surfaces per point charge is just the series of concentric spherical surfaces, okay? Alright guys, so let's do, so that's about it for review.